All right, so we're going to test the claim that the average heart rate of ICU patients is at most 95%. Okay, so a couple things here that are key words to figure out what's going on. We have the word average in here. So, pen, average means I have a mean, right, mu. And at most. So let's see, if my wife says, hey, you can go to the hardware store, but you can spend at most $100. Okay, so shit, I can spend $100, right on. Or I could spend less, but I can't spend more. So at most means less than or equal to. So that is an important thing to figure out what the claim is telling us. Less than, greater than, less than or equal to, greater than or equal to, not equal to. Those are our options. And at most means less than or equal to. And sometimes it's obvious, sometimes you gotta really think about it. All right, so the claim says mu is less than or equal to 95. So putting that in math speak, since there is an equal to in it, this has to be the null hypothesis. So the notation is H subscript 0 colon mu, because it's an average, at most is less than or equal to, and then the number 95. The alternative to that would have to be then that mu is greater than 95. Okay. Now they're giving us a significance level of 2.5%. That's a little less than 5%. And again, heart rate is a big deal. ICU is a big deal. So we would probably want a significance level of less than 5%. So they're telling me there that the cutoff for an unusual event is 2.5%. Okay, so again, this is a cutoff for an unusual event. And that's assuming that the heart rate should be less than or equal to beats per minute. All right, so we got the setup there. Quick sketch on this. Is it a two-tail, left tail, right tail? That always depends on the alternative. Since it's a greater than, this would be a right tail test. And a rough sketch looks something like this. Oof, not very symmetric, but it's my best today. Mu is 95, goes in the middle. This is a right tail test, so my data ought to be out here somewhere. The question is, how far out is it? Is it close enough to 95 to say, it's close enough, or is it far enough away, meeting the rare event rule, in this case, saying, ooh, no, that's bigger than 95. Huh, interesting. Okay, so back to the problem. And let's blow this sucker up a little more. Let's see, click, control plus plus plus. All right, so then we have to decide which one do we want here. So we want a mu, not a p. And it looks like it's the first one. Mu is less than or equal to 95. That's at most. And then here's the other. Okay, just make sure. This one says mu is greater than or equal to. This one says at most, so that's the wrong null. This one has a p, that's wrong. P, that's wrong. P, that's wrong. Mu equals, that's not right either. Okay. So I'm pretty sure I got the right hypothesis based on my initial assessment. The alternative hypothesis, in this case they're calling it H1, is greater than, so that means this is a right tail test. And hang on 1 second. Excuse me, I got something. Sorry, homeschool question. We're in woodshop today in the background. Okay, so right tail test. Okay, so now I have to go get the data. So in this case, it says use the stat key data, switch the data to ICU admissions heart rate, and make sure we set the null to 95. Okay, let's go for it. So we jump in, and body temperature, nope, that's not what I want. I want ICU heart rate. And if otherwise, we might have to copy and paste data with the edit data. And there was at least one problem like that, I think. Maybe not. All right, this says mu is 72. That's not what I want. The null hypothesis is 95. And don't worry about that their null says equal to and ours is less than or equal to. That's not that important actually. It's the alternative that's important, which is the test we choose. So that's okay. They have a sample mean of 98.925. We'll use that in a moment. So again, you can run your simulation once you have the right data and the right null hypothesis, and then you just start generating samples. So generate, get at least 6,000 in there. I'm gonna do 7,000 this time. My alternative was greater than, that's a right tail. And then I plug in the sample data. And the sample said the mean was 98.925. So that's on the x-axis, 98.925. And the results will differ slightly each time because this is a randomization, like drawing cards from a deck, but we've done it thousands of times, so we should be in the ballpark of each other. So this time I get a p-value of 2.1%, which is slightly less than the 2.5%. So that means this is a rare event. If it's a good random sample, that means there's something wrong with the null hypothesis. It must not be true. So we have evidence that average heart rate of ICU patients is greater than 95% is what this tells us. So my p-value is small. So let's put that in the sketch. And again, anytime you do one of these problems, you should be creating a sketch. You should be writing down what each variable means. I didn't write that. That was in the claim here. So just to be clear, what the heck is mu here? Mu is the average heart rate. I am recording this, yes, of an ICU patient. Okay. And we found that our sample data was 98.928 beats per minute when we were expecting, welcome Jennifer, 95 beats per minute. And the chance of getting a sample that's 98.928 beats per minute or higher, the probability of that happening when we were expecting it to be 95 beats per minute, I got a 2.1%. And that's what we call the p-value. And the p-value is always based on the sample data with the null hypothesis in the middle. This p-value is less than my cutoff, so that is less than alpha. Alpha here was given to me at 2.5%. And sometimes on these problems, your data isn't, right? So in this case, my p-value is small enough, so I do have a small p-value. If your p-value is small enough, then you get to reject the null, which means the data favors the alternative. Okay, so let's look back at the problem, and then I'll write a written statement for the press on this. Week 7 practice. Okay, so I got a p-value of 0.021. Notice there's no percent symbol out here, so I had to enter it as a decimal. Based on this, we reject the null hypothesis. Ooh, and I wrote up a couple of conclusions. Now we have to pick the right one. All right, I think I'm gonna go write it by hand before I try to pick one of those, because sometimes this messed up, some of these are just messed up and can be easily misled. So I'm gonna write a conclusion. New page. All right, so let's see, I might as well start it off like that one did. Let's use blue. So based on this sample, there is sufficient evidence to reject, I'm gonna make this a little more formal than the last one, a claim that the heart rate of ICU patients is at most 95 beats per minute, and accept the alternative at the average heart rate. Ooh, I didn't put average earlier. That it should be average heart rate right here. That the average heart rate is greater than 95 beats per minute. Okay, do we know that it's 98.925 on average? No, that's just the sample. All right, so which of those is close enough to that? So based on the sample data, there is not sufficient evidence to reject. No, we do have sufficient evidence. Okay. Now, if your p-value came out to be greater than 2.5, then you would not have sufficient evidence, but then we got to read the rest of the claim. So let's see, just in case, based on the sample data, there is not sufficient evidence. Actually, let me get my pointer out here. Oh, it doesn't work on this screen, bummer. That the average heart rate of ICU patients is at most. Yeah, so if our p-value came out too big, like 3% or 4%, then this would what we would have to select there. All right, so let's see about this one. Based on the sample, there is sufficient evidence to reject the claim that average heart rate of ICU patients is at most 95. Okay, so reject the null and accept the alternative claim that the average heart rate of ICU patients is greater than 95 beats per minute. That looks pretty damn close to what I wrote. I'm gonna check that for now, but I'm gonna still double check. Based on the sample data, there is sufficient evidence to reject the claim that the average heart rate of ICU patients is at most 95 beats per minute. That seems like there is sufficient evidence to reject, and that looks like the null, and accept the alternative claim that the average heart rate of ICU patients is 98.92. No, 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 we can never say for sure that's the actual mean, so that's bad. Okay. Based on the sample, there is sufficient evidence to support the claim that the average heart rate of ICU patients is now. We can never say something is. That's nonsense. Okay, so the third one's nonsense. This one's nonsense. The second one is a good conclusion for rejecting the null. Yeah, and the first one would be failing to reject that. It came close enough to 95. So it's this one right there. In my case, yours might be different. Again, every time this problem regenerates, it gives you a slightly different scenario. Let's see, did I do that right? Yep, and I feel like getting some green check marks, so I'm gonna hit submit. Cool. All right, that was a tough one. I do highly suggest that even on the problems that ask for decision but not a conclusion, that you take the time to try and write out a conclusion about what the situation means, what our decision means for reality. Okay, other questions? Got nothing in the chat at the moment. All right, so a couple of reminders if there's no questions. Be sure to read the examples in the book. The beginning of the book talks about, actually I already had it up there, what it means to be a hypothesis test, how one writes a decision, how one writes a null and alternative hypothesis, the things about what symbols can be in a null or what symbols can be in an alternative. They talk more about how to decide on the type of test. So these are just examples of what a null and alternative is. And then they get down here into the possible ways to make a mistake and what those mistakes mean in reality. And those are hard questions. I have to draw a table out like this every time I want to analyze that. So maybe I could do that for ICU patients here. Yeah, why not? Let's do that. And then after they talk about all the different ways you can make the error and what those errors mean in reality, it's one thing to say, oh, you have a type 1 error. Well, what the hell does a type 1 error mean? Right? My mom would want to know that. We're skipping most of 9.3 for now, but then 9.4 is more about that rare event rule, which is kind of just drawing that line in the sand to say, okay, when do we have evidence to reject, when don't we? And then the rest of the chapter is just doing hypothesis tests. Then after that, I have a bunch of pages on how to state stuff, how to draw stuff, how to use stat keys. So again, be sure to take a look at those examples. So for example, these two models right here, the model for a hypothesis test for a mean with stat key and a proportion with stat key, I walked through the whole procedure with screenshots and pictures and explanations. So be sure to read those pages there. So let's try to do a breakdown of the type of errors we could have just made with this ICU patient thing. All right, so possible errors. In the decisions we make. To figure out what these errors mean, I always have to make one of those two-way tables, contingency tables. And the typical way of drawing them is like the book has. The columns are the truth about the null hypothesis. In other words, what's the background reality? And we're always trying to discover what is the true reality, and we often never know. We just think something's true. We never know for sure. So in reality, either the null hypothesis is true, oops, to write true there, or the null hypothesis is false. So what would that mean in this case when I'm talking about mu is the average heart rate? Average beats per minute, ICU patient. If it's true, then I would expect that the average heart rate is less than. So mu is less than 95 beats per minute. Oops, beats per minute. And if it's false, then I would expect the beats per minute to be greater than 95. And a high heart rate is dangerous unless you have a reason for it, like working out or fear. But it should go back down to some normal heart rate. And normal heart rates for people, let's see, what did I see? It's somewhere between like 60 and 100, like 80-ish is in the middle for your average adult. That's a wide range of ages, you know, like 20 to 80. And then over here we have the test. And with the test, make sure I got the order the book uses right. Oops, come here, book. Right there, okay. Reject, fail to reject, and then reject. So fail to reject, and this one is to reject the null. So those are my rows. All right, so if we fail to reject, what does that mean? That means that the sample was close enough to 95. Beats per minute. And the rejecting the null means the sample was far away. Sample, oh, come on, pen, was greater than 95 beats per minute. If I fail to reject, that means my data supports the null hypothesis. If the null hypothesis is true in reality, then I made a correct decision here. So this would be a correct decision. if I say, hey, my sample says it's, yeah, average heart rate of ICU patients is higher than 95 beats per minute, that means I made a mistake here. So this is an error. This kind of error is what we call a type 1 error. And that's the value alpha is what we guess at the percent of making that, the probability of making that mistake. I still haven't gotten to what they mean. I'm just kind of getting into what's right, what's wrong. If my sample again showed that it's close enough to 95 beats per minute, but the null is actually false in reality, then I made a bad decision here. This would be another error up here. This is what they call a type 2 error. They usually give that the letter beta, sometimes referred to as the power of the test. And then down here, my sample says, hey, it looks like the beats per minute is higher than 95. In reality, the null is false, it is higher, and so I did make a correct decision over here. And then the question is, well, what are the consequences of these errors? If I made the right decision, I made the right decision, good job. But if I made a mistake, okay, so I here, my sample says, nope, it's greater. So that means people that come to ICU have a high heart rate. And that's a sign that something's wrong, right? But reality is, no, it turns out people in the ICU don't necessarily have a high heart rate. So if somebody comes in with a high heart rate, I say, oh, you have a high heart rate, we better check you in. Okay, all right, so we check them in, nothing's wrong. Oh, okay. Over here, what happens here? So here we say the average heart rate is, it's around 95. So here, average is 95 by sample. So our sample suggests that people that go to the ICU don't have a higher heart rate. So let's see, but they really do. Because the null, let's see, no, I'm not analyzing that right. Something went wrong there. My sample says it is 95. So the people that come to ICU, my sample suggests that people come to ICU don't really have a high heart rate, but the reality is, but reality is they do have high rates. So my sample suggests, don't worry about heart rate. Somebody comes in with a high heart rate. I say, it's probably no big deal. Then they have a heart attack. Ooh. So I'm leaning toward the type 2 error being the worst error based on the consequences of the conclusion. And that's always a hard thing to figure out. Some days I reason through it incorrectly. So I think this is worse. Feels like that one's worse to me than this one over here. Okay. So that's the point of making one of these tables, to try and decide which error is worse. And to do that, you got to kind of figure out, well, what does it mean for the null to be true? What does it mean to the sample suggest one thing or the other? And then if we put those two things together, what the sample said and what the truth is, which could lead to you misleading people in a worse way. And again, that's a tough one to figure out. I did an example of this yesterday where I talked about tainted water and a test saying the water is or isn't tainted based on the reality that the water is or isn't tainted. So feel free to take a look at that recording from yesterday. All right, so I think that's enough for today. If you have further questions, remember you can always message me through Canvas or use the message instructor button from the homework problems. And I'll be back tomorrow at this time to answer more questions if you have any. These are really tough problems. We're going to spend the rest of the quarter talking about these problems. So next week is more theory about this. The week after is more practice with hypothesis tests. And then we're done. The final week is just the final exam. So take care, do good math, stay in touch. I'll see you later.
Thank you.
You're welcome. Bye-bye.
Bye.